right, welcome those that are online. Looks like there's a little lag in the this. Hi, welcome to class. Any questions anybody wants me to address before moving on? Yes.
Do we have each given to us?
So do you have the formula sheets handy for the exam? It's open note, open books. So just have it handy for your own. So I won't have it on the exam, but you will have it accessible. Yes.
So a question kind of from the quiz.
Uh-huh.
So when we have a circuit with a 9 out of 10, we were analyzing P with 0 loss. So immediately after the circuit, do you consider like a voltage source or a current source when finding IC?
I don't know what you're going to meaning. Let me grab something. Right, so this was the quiz. This is an example of quiz question. So you're saying on this one?
Yeah, on that problem, we're looking for an IC.
Okay. So the question is for those that are online, and anybody else who couldn't hear that. So the question is on this one, if you're looking at time 0 plus, which you have to first look at 0 minus first. So if we look at 0 minus, the switch will be closed first. So it would be in this position. And this is going to be an opener. And this one would be a short. And so you would solve this, which is going to be the voltage. Hopefully you can see the voltage here is going to be VC. And so you would do -4 plus VC minus VS over R2 and solve that for VC. And then from there, you would redraw the circuit in the 0 plus. And for this one, then it becomes an open. And this becomes what? A current source, correct? And so you have your current source. And this is open here, so that's 0. So you have a 0 amps there. And this becomes what? The, thank you, voltage source. Of the value of 4 R2 plus VS. And so you're asking to find the initial values and then also need the initial value for, is it VL? I can't remember what it, IC, okay. So this will be the one you'll use IC of 0. So what will that be? It'll be the current source is set to 0.
So it doesn't matter that voltage source there. Yeah, why wouldn't that?
So your voltage at VC here, relabel this a different voltage because it's no longer VC. So you're going to have voltage drop across, I'll call it VX. So there's going to be voltage drop across that current source, but there's no current flowing through it. So this voltage source adds voltage here and here. So you have, call it V2. So VS and V2 add up to give you the value for VX. You have no current though going through the current source branch. So IC0 will be 0. You have voltage across the VC and you have voltage across the current source. So you can have voltage without current there. It's just like a battery without hooking up the battery to a circuit. You can measure the battery, but there's no current flowing through it until you hook it up into a circuit where you have a loop. Does that make sense? Yes.
If we look at Ohm's law, like current is equal to voltage divided by resistance, and if there is voltage and resistance, wouldn't there also be current?
So yes, and there is current because of the what's called the parasitic effects, where with a wire you actually have, you know, a little resistance. So your voltage is like super, super small. It's 0.00001 maybe instead of 0 volts, you know, but that's more from the parasitic effect of what's going on. So here, yes, if I was to actually go build this, there's going to be a little current there. It's not going to be 0, but when we model it and we analyze it by hand, we're going to set all those to an assumption until we build it. And then when we build it, we're going to look at those parasitics and those other effects. Does that make sense? Okay. Answer your question?
Yeah.
Okay. So I know that concept is a little bit, because you're like, there's a voltage in there, so that generates current, but because that source is there and it has to stay the same, that inductor acts like a resistance to not have any current flowing through it. Okay. Other questions? Any questions online? my chat window so I can make sure to see it. Okay. All right, so yes, another question. No worries.
You're the same way in the past, during source there. Let's just say it was on, then would we consider IC?
So if it was a wire, say the inductor was not there and there was a wire instead of the inductor there would be current through there. So you would have to find the current going through the R2 and VS branch. And then that would be the voltage there. Or then it would be the opposite current because it's all one branch. Does that answer?
Yes.
Okay. Any other questions? Okay, so I've done a lot of examples of series connections so far in RLC. So now we're going to work a little bit more on the parallel examples here. Thursday, again, you'll have homework due and your discussion will be due. Friday will be another quiz. Next week will be your exam 1 group. Homework will be due by Tuesday. So make sure you've put yourself into a group or joined a group. If you want to work individually, again, that's fine, but move yourself into the individual group so that it's known that you're going to work as an individual for it. And for that preparation, you're going to create a problem, an RL problem or RL circuit, solve it, RC circuit, solve it, RLC circuits, at least 2 of them, series connection, parallel connection. So those are what you're going to create to help prepare for the exam. So again, if you're an individual, you can prepare your own problems, solve them, post them, give feedback on other people posting their problems. It's due by Tuesday, but I encourage you to do it earlier, work with your groups because it is a good help and preparation for the exam. The other thing that you can use for the exam is that Unit 1 practice problems. They're extra credit for homework if you need, but they're great problems to help prepare for the actual exam. So use that to also get extra practice that you're going to get practice on the types of problems that I ask. The book problems as far as assessments, you can use also, and they have those solutions. I'm trying to make sure that all of the problems you've done so far, your quizzes and your homework has all of the problems, not the exact solution, but at least the method on there. And a couple of people have pointed out, sometimes I have an error, I'm missing like an authorization on one, so I need to re-upload that file. If you see errors like that, let me know. There's a lot of problems. And so hopefully that will be also helpful to get that feedback. It won't be the exact numbers, but it will be the method and the solving of the methods. So like you can go and check like, how did I get IL0 initial value and why? All right, any other? Okay, so exam will be next Wednesday, so in a week. So start getting ready for that, start preparing. It will be those 4 types of problems: RL circuit, RC circuit, RLC circuits with series connections and parallel connections. And then I typically ask like an understanding question. Those understanding questions are again ones that I'll put into that Unit 1 practice problems. So you won't really see those anywhere else, but that's a good place to also see examples of those. All right, so let's just also reiterate quickly steps on solving these type of problems that are RLC problems. What's your first step? Before RTH. Correct. I mean, you can do RTH first, but typically I do series or parallel connection. So identify what kind of connection do I have, series or parallel. And then from there, what do you put the circuit in to find that one? Okay, good. Final state to figure out if you're in series or parallel. Then you need to find RTH. And that again is going to be which initial or final value. Final circuit again. And that one you're going to find RTH from. And so you'll find what next? Alpha and omega. Then what? Do what? Correct. So then you have to identify what characteristic do I have? Critically damped, underdamped, or overdamped? Then what? Do what?
Solve the circuit.
Then you're going to solve the circuit to get the values you need. So if you're, for example, in critically damped, you're going to find VC 0 and VC infinity and IC 0. If you're in the others, you're going to find, if you're in a parallel connection, you're going to find IL 0, IL infinity, and VL 0. And so whatever value you need to find, you're going to draw that circuit in that stage. What is kind of the trick that you need to be careful about for initial values? So if I'm in, for example, in critically damped series connection, I need to find IC of 0. What stage is that going to be?
That's the transient state, right? The 0 plus.
Yes, so I need to make sure that I've found 0 minus. Use the values from the inductor will be changed to a current source, voltage to a voltage source, and then solve for IC of that circuit. If it's in series, a lot of times that's going to just be the IL value that you found from IL 0 minus, but not always. So you just need to make sure you understand that. Okay. And then from that, hopefully you have all the values. You just plug them into these equation sets. Where did these equations come from? The textbook. But where, how were they derived? What created them?
If we
Second order model.
Correct. So we set up the circuit of equations from voltage loops, current summations, and we use the differential description of the components. So for C, it was, or for capacitor, it was IC is equal to C dV dt. And for voltage, it was IL was equal to IL dt. And so use those, and it became a second differential equation. And we had 2 time-dependent elements in there. So that is where these equation sets come from. And so from there, it was algebra after that, but then you had to use separation of variables, so that technique, in order to get there. So that's kind of what you've done in lab, is those steps also. So next step after this is what happens now. These only had an RL or an RC. What happens if we have two Ls, 3 Ls, 5 Ls?
It depends if they're series or parallel, right? But then you can
Correct.
combine them.
So say they were not in series or parallel and I have elements in between them, so they can't be reduced. I would have, if I have 5 time dependent elements in my circuit, I'm going to have a 5th order differential equation. So for every element that you add, you get a differential portion of it. And that becomes then like a differential 5th order differential equation. So those become harder to solve. So we're going to learn some techniques next on how do we actually solve those circuits in an easier way that you don't have to go through all the derivations. So I'm not going to make you do a 5th order differential equation solution. So there's easier techniques, and that's going to be our next steps after this section. So getting you a little prepared for the next steps. But first we want to make sure you understand these steps on solving the circuit. So let's look at this circuit and go through these solutions. So first step is to do what? Parallel or series. So infinity is going to be closed for this one. And the inductor becomes what? So if I'm just looking first to say, am I in series or parallel? Hopefully, what do you see here? They're in parallel here. So parallel form. And so this means that I am going to use this equation for alpha instead of the series RLC. So with that, I need to find RTH. And so for RTH of this circuit, Our independent sources, when we take a Thevenin, are set to 0. And so that means that this source will become a wire and this becomes an open. And then I look at my A and B of these. If I don't see it, hopefully this is an easier one to see, but if I don't see it all the way, go back to highlighting with colors, the extraordinary nodes. So on this, I can see like, oh, everything in between the two colors have to be in parallel. So from this, I can see that my RTH is what? Three parallel with 6, correct. So correct, 2 ohms. All right, now I need to know alpha and omega naught. C is 0.5 milli. And omega naught is 1 over the square root of L, which is 2 milli. And C is 0.5 milli. Let me find the. All right, so alpha ends up being 500 meters per second and omega naught is 1,000 radians per second. Was this 500? Anybody see that? What was it? Yeah, let me find the other one. It was alpha, 500 meters per second. Okay, so from here, what do we do? Okay, so we see that alpha is less than omega naught, so we're underdamped. So from this, I use the parallel side, which is this one. Oh, I have them down there. And we're going to use this equation set for underdamped. Oh. So we need WD. Which is the square root of omega naught squared minus alpha squared. Uh, 866 radians per second. All right, so T equals 0 minus, so we're going to do the initial value. So actually going back to this equation, so I need initial value, final value for IL, and VL initial value. Yes.
Regarding RTH, where would our A and B values be? Like, where would we be calculating from? Would it always just be the capacitor?
So because they're in parallel, it's going to be across both the L and the C combined. So this whole wire that's purple on the top is A, and the whole wire on the bottom is B.
Then can't you just say RTH is like 3? It's like, if we just look to the left.
sort of going right? Like just 6?
But I can redraw. I mean, this circuit can be redrawn with, because the wire is there, I can draw it as this. That would be the same. And you could see there maybe that 3 has to be in parallel with 6. Or I could redraw it as this. These are all the same circuits.
But A and B, you're saying it's like in the capacitor or like the inductor. Not the electrons, or some go left instead of going right.
They'll go both ways. So I think they'll always go both ways. They'll take any path from A to the B.
But then, well,
So you have to go through all of the pathways. You can't just go through one. So you have to go through every pathway from that node back to the other node. And so that's why they're in parallel, because there's 2 pathways. If there was not a 6 ohms there and that was open over there, then it would only be 3 ohms for RTH. But for RTH, you have to go through every pathway from the node you're looking at back through the other node. And so because there's more than one, there is the pathway through the 3, and then there's also the pathway through the 6. If there was another branch, we would have to go through that pathway too. And it can be, I mean, it could be connected crazily anyway on here. Like I could have another one that's connected here. And I would then have that resistance in parallel with 3 and 6. Does that make more sense?
Yeah.
Okay, so make sure you do calculate all pathways from one side of it to the other side of it. It's not just one because it looks easy to go just to the left. Does that make sense?
Yeah.
Okay. So when they're in parallel, make sure you are going through every pathway to back to the other side of it. All right, any other questions? Okay, yes, Thomas.
So it says ICT, or you're just doing ILT. I guess it's determine ICT in the circuit.
Uh-huh.
Looks like you're trying to look through the inductor.
So yes, so we'll get to that in a minute. So to solve that though, we know that the equation set is only used to find IL of T. So we can use that. Once we find that, then we'll find IC.
I was just wondering because on the RTH you open both of them instead of shorting the inductor and opening the capacitor.
That was just to find RTH.
Okay. Do you do that for no matter what for RTH? RLC?
Yeah.
Okay.
So for RTH, you're going to kind of remove those elements and put an A node and a B node.
Okay.
All right, any other questions? Okay, so going back to the initial value. So initial value is found right before the switch moves. So the switch is first open and then it closes. So this will be in an open position. It's sat there for a long time. So short this one and open this one. And from this, I need to find the values for VC of 0 minus, which will be what? Correct, because there's a wire across it. So it's got to be 0. And then IL of 0 minus.
Sorry, can we explain why VC is 0, 0? Is it the short to the left of it?
Yeah.
Okay. Yeah.
Again, if you don't see that, you can kind of highlight these nodes again. And as I highlight that, I see like, oh, this wire actually goes there, all the way. And so because they're the same color on both sides, it's got to be 0. So if you visually see it, great. If you're still not visually seeing it yet, go back and highlight all of your extraordinary nodes with colors. And so then hopefully you can see it from there. And that, again, just takes lots and lots of practice, and eventually you won't need to color it, but until you intuitively see it, keep coloring it. All right, so IL of 0 minus will be correct. And why is it negative 6 amps? You are correct. What happens to the 6 ohms? It's bypassed or shorted, so there's no current flow in that, right? And so all the current that's set at 6 amps has to go through that IL. And then you hopefully see it's in opposite directions, so you get the negative. Okay. Correct, yeah. So the 6 amps is forcing it from top to bottom. And if you follow it around, it will go up through the IL, but the IL is marked as going down, so you get a negative.
So real basic question, on the current source, what's the polarity of this? Like, is the positive where the arrow is, or tell that?
Negative is always on the arrow side.
Okay, so it's opposite of the. But yeah, that makes sense, I guess, that's all.
So typically I label this direction. So that would be plus to minus, and then the current would be going down. And so across this would be your VL. Okay, any questions on those values? Okay, this is hopefully an easier one to solve. If not, use node voltage or other ways of solving the circuit to find those values. So once I get those two values, I'm going to use those to actually find the initial value at this stage. So here, this is now closed. And this acts as a current source with 0 again. And this acts as a voltage source. Oh, whoops, that's not 0, sorry. As minus 6 amps. So I keep the direction of that current source the same as it was in the direction I solved the L for, or IL for. And then this was 0 volts. Okay, so from this, my initial values, I needed to find IL0, IL infinity, and VL0. So VL is going to go in this direction for polarity. And what will that be?
You have to solve it. Well,
If you do have to solve for it, if I mark these, I note that, again, this is all the same wire. Do I know what the value is here? 0 volts, correct. And VL is from purple to green. So what will that be?
also,
0 volts, correct. So there's your initial value for VL. IL,
that 24-volt source won't affect the 0 volt, like the voltage of the L.
so what happens there is that you have 24 volts here, and then you drop 24 volts across this to make it 0. So if I was to take a loop, I would go through the 24 volts, 3 ohms, and through the 0 volt source. And that loop will then create that I have to go up and then drop 24 to make that 0. Yes.
I know for this problem, we're not looking for IC, but in this case, would we use like the noble analysis to find it, or?
So for this one, you would do a current source, or sorry, current summation. So what's the current here? 0, right? Because there's 0 volts across it. And then you would need to find the current here. And then you could do a current summation to find IC. Mhm. All right, going back to IL 0, what's IL here going to be? -6 amps. Okay, so those are my initial values. And now I need my final value. So it closed again. And this time it's sat for a long time. So that's closed and this is open. So this becomes a little more complicated because I kind of have this now at more of a ground position. Yeah.
I didn't have the intuition to see that the current source going through the 6 ohm resistor is 0. Would it be possible to demonstrate that mathematically?
Say that again. Which one?
Could we prove or show how that the current through the 6 ohm resistor is 0?
You know that 0 volts is on the top, right?
Right.
And so if you were to do node voltage equation for that current in that branch, what would it be?
It would be 0 minus the 6 ohm resistor, or 0 minus, well, yeah, 0 over the 6 ohm resistor. Okay, so that
Which is 0.
Wouldn't affect that.
Correct.
Why?
Because you have a wire in parallel with that resistance.
Okay.
So, but mathematically, if you don't see it, and you know that voltage across it,
Yeah.
just do 0 over 6.
Thank you.
No worries. Okay. So this one looks a little bit more complicated to figure out what IL infinity is. So for these, I usually suggest making a Thevenin equivalent of the circuit. And then from there, I find it to be easier to solve. So for the Thevenin, we are wanting a voltage and a resistance. And in this case, then I'll put the A and B is going to be where the inductor and the capacitor are. And so I'm going to kind of open this up and if I can erase the purple, there we go. And now they're different nodes, so it makes it easier to look at. So here with the node, it will be A on the top and then B on the bottom. I already found RTH before. And now I just need to know the voltage to finish this, which is going to be the VTH at the top to the bottom. So I can just do node voltage here quickly. So VTH minus 24 over 3 plus VTH over 6 plus 6 equals 0. What's 24 divided by 3? 8. Is that right? So that's 2. So this ends up being 4 volts. 4 volts. So this is 4, and then we already found that to be 2 ohms. So now I have, I can put back my inductor, which is going to be the wire, and the capacitor, which will be an open, and I'm just solving for IL through this. And IL infinity is going to be what? So 4 divided by 2. So 2 amps. And how do I know if it's positive or negative? So with it labeled in this direction, I can go and just do a quick loop to see that that's going to be a plus VTH and then minus IL times R. And so that will give me a positive value for IL. So it is a positive 2. All right, and this is infinity. And so I have IL0 was -6. VL of 0 was 0, I think. Yep, VL of 0 was 0. And IL of infinity is 2. These are in amps. And so my WD I found above was 866 radians per second. Alpha was 500 meters per second. And omega naught was 1,000 radians per second. So I plug these in into the equation set. I get D1 is -6 plus 2 or -2, sorry. -2 for -8. And this one, this becomes 0. And so I have 500 times -8 over 866 for -4.62. And IL of T and so this gives me IL, but the question had asked for IC. So how do we get IC from this?
We have to relate, yeah. Relate.
Yep. So how do we relate IC to IL? So IC is equal to what? Correct. And then we know that VL is
Yeah.
and the voltage, because they're in parallel, are equal. VL equals VC. And so if we differentiate VL, that's equal to differentiating IL twice. And then we can plug that in here. So we can do IC is equal to C. And then take the second differentiate the IL equation twice. And that will give us the IC.
What do you recommend?
I can't remember what I used for this one. Which one? So Wolfgram alpha is one that's I used quite a bit. And somebody else mentioned that one. Okay, so this ends up being okay, there you go. Yes. So, oh, yeah. There, that should be there. I did do that in the actual calculation, but yeah, it should be LC D squared IL DT squared. I missed the squared there too. All right, questions? You guys ready to do these? So for these problems, I actually think that Thevenin for that IL infinity is the easiest because then it's not as confusing to try to figure out and do a current summation into a ground wire. That always tends to confuse students. So I think try to take that Thevenin. It was only one extra step in there, but I usually suggest doing that. All right, so go ahead and break up into small groups and work on solving this one. Remember first to find IL of T first. Yes. Yeah. So his question was about the IL. That was just because that was given to me as the label. If it's not given to you and you're just trying to find that current, you can arbitrarily choose which direction. There is no right or wrong on that one. Any other questions? Okay, go ahead and break up into small groups. You guys online, you guys can work together or individually. There's quite a bit of individuals on today. Do you guys want to work in this main room or do you want me to put you in a breakout room or breakout rooms for smaller groups?
I'm fine working in here.
Okay, any other requests, comments? Okay, you guys go ahead and work together as a group. Okay, great. Yes. Sorry.
Thanks so much. So, no, I was doing like the, this one. So, I was like, kind of place on this one, way to sort of, yeah, and I'm like, is it going, is it going down?
And then whatever direction you stay, you're gonna solve for them. And you're either in so it'll be a tough plan. And then you're gonna keep that direction and you go So it doesn't matter, CIC. Yeah. And then draw that sword. Value. Yeah. It's like, you're gonna say, and I thought for that. Robert. Oh, shoot. Find the value. Going down. Yeah.
So what it's like,
But, you know, the value of your, yeah.
looking at something that moves out. It may not all be general, so maybe it's not. I'm way off that. Yeah.
And go back to like. Maybe at this stage. And then. And I do understand that.
Well, thanks for zero
Thank you. Don't flip it around. So, knowing some word, I'll, okay, well, I was gonna, is that?
All right. Have you guys gotten far enough to find alpha and omega naught? Okay. For those that have found that, what characteristic are we looking at here? And so critically damped is correct. Okay, just make sure you guys keep working on the same direction.
Anyone you got negative 500.
Okay, right?
Okay, yep, that is correct.
Alright, I just have a question. So my thought process for kind of how I'm doing that, once we get the
Yep.
then define, so VL equals BC. So to get VL, we find the derivative times inductance. And then to find BC for IC, we have to find the derivative of this VL in times of like capacitance here.
Yep. All right, so steps to solve for this. So first step, identify what? Parallel or series, so which is it in this case? So it's the final position, which will show you that it is in parallel. So I also had another question. I do want to make sure that you do understand these tables. On the left side is for circuits that are in series. Those are the equations that you can use. And on the right is when you're in parallel. You would use the equations on the right. So just want to make sure you guys are clear on that. So a side note on there. Okay, so parallel form, critically damped. Now what? Okay, great. So RTH, in this case, RTH is going to be what? 500, correct. And then alpha is 400 and omega naught is 400. So that's where you get that it's critically damped. All right, so then from there, initial, we do T equals 0 minus. So it's open first and then the switch is closed at 0. So this one is going to be open, capacitor's open, and a wire here. And so IL will be what? 0, and VC, which is here, 16 volts, correct. So here I replace this with 16 volts. This becomes a closed, and this becomes a 0 amp. Or you can leave it open, whichever way you like to view that. So I need to know from here, IL at 0. Correct. And then I also need to know VL. Correct. So you have 16 volts. And then the final position is again closed. This becomes a wire and this is an open. And so to make sure my polarities are right, I can just do a loop. Plus 16 minus IL times 500. And so 16 over 500 is 32 milliamps. And then here I'm going to have IL of 0 was 0. So I'm just going to have a minus 32 milliamps. And here I have 1 over L times 16 plus 400 times minus 32 milli and gives me minus 6.4. All right, so from this, I'm going to solve for, I just plug in the B1 and B2. And that gives me the equation for IL. And then I have to differentiate IL twice. So if I differentiate IL one time, you guys remember the properties of the exponent raised to a number, differentiating it? So in this case, it's going to be what will be the first term here. And then for the 6.4t and the e to the minus 400t, I need to take the first one and then take the, or leave the first one, take the differentiate the second part. Oh my, I can't talk very well today. So minus 6.4 milli or t, and then I bring down the minus 400. And then I differentiate the first part, which will be 6.4. And then the 32 milli goes to 0. And then I differentiate this again. Oh, this gets long. First, second, and then I leave the first. Feel like I made an error somewhere. Okay, so the first one just differentiate, so I bring down to minus 400. The second one, I do the first part and leave the second. And then I have to take this, the first and then differentiate the second part. Okay. And then that ends up adding up all of those numbers to just be minus 6.4t. I don't see, I feel like there's an error somewhere, but anyway. Multiply that by LC, ends up being minus 6.4t, e to the minus 400t. All right, questions? Okay, you guys ready to do the homework? So this is gonna be more homework. Yes.
We need to do the road on that. We're always out for like ILC.
I typically always just ask for ILFT.
Okay.
Okay.
I won't make you do a double derivative on the spot.
I think you. By the IL prime, that minus 6.4, minus 400.
Yeah,
I don't think that.
but when you take the derivative of that, you have the first. And then you bring down the minus 400, e to the minus 400t.
If IL is like that, then you'll take, you'll have one derivative here, then another derivative here, but you have a third one. Because you have the minus 32 derivative here, the minus 6.41 here, but you don't have, where's that other one coming from? That third. That,
So this is, I leave the first component, which is minus 6.4t, and then I differentiate the second, which is minus 400,
Yeah.
e to the minus 400t. But then I have to take the derivative of this portion
oh, the
and
T,
leave the
yeah,
second.
oh, never mind,
I don't know. I'll
yeah,
have to look at it. more.
no, that looks correct.